So we'll, the title of the talk is Roughness. Just let me know if you cannot read out the words. We will quantum gravity. This is based on a joint work with Zeitouni Fan from Peking University. By the time we were writing the paper, he was a senior undergraduate there. So unfortunately, I have to give some backgrounds to the thing. So what is Liouville quantum gravity? I mean, it was very broadly speaking, it's a one-parameter family of random fractal surfaces, which was first studied by physicists in 1980s, starting with Polyakov's famous paper. So very formally speaking, and I'll write down as much as time permits. It's a class of canonical two-dimensional Riemann manifolds. Okay, so now for the parabolist, in the last decade or so, it has emerged to be one of the most active and fruitful areas of research. So formally speaking, let's see. So as I said, it's already parameterized by a parameter gamma. Parameter, let's call that gamma. Gamma Liouville quantum gravity. We'll abbreviate it as just gamma OQG surface is a random, within quotes, Riemannian manifold, because it can turn out to be not so. This is just a formal description. With the metric tensor given by e to the power gamma h ds2. ds is the standard length element, where h is some variant, sorry, some variant of what is known as a Gaussian free field. I'll not actually go through the formal definitions much of H, but I will, of course, go through the relevant properties, and that will give a good idea what it is. GFF on some domain, subdomain of complex numbers. Okay. Okay. So, well, first of all, what's the problem? The first problem is that H, the Gaussian free field, is a random scores distribution. Okay. In particular, this thing, as it's written, you know, if you remember the standard interpretation in Riemannian geometry, you need to get the lengths of paths, you just need to get this conformal factor along it. It doesn't work because it's not realizable as a pointwise function as such. Okay. So, and just like in Riemannian manifolds, you have, of course, a length. The met is a metric length and associated area measure. Okay, of it. So, so the first rigorous work, I mean, in the probability theory, started off with understanding the associated area measure, okay, the volume measure, which is called the Liouville quantum gravity area. And it was started in this famous paper by Duplantier and Scott Sheffield. Paper came out in 2011, but it's appeared before that, where they defined the LQG area for all gamma and 0, 2. You can disregard this trivia for now, but I'll come back to that later, the so-called subcritical bridge. And the construction was based on an object called Gaussian multiplicative chaos, which was kind of like obscured but already discovered back in 1985 by Kahan. Okay, so that's, sorry. Now, the construction of the metric is much more difficult. I mean, it's already very involved, but especially because you, if you want to define a metric using a formulation like that, you have to consider, optimizations. Like you have to, if you want to find the distance, how do you define a distance from a tensor like that between 2 points? You optimize the integral by in whatever sense over all possible reasonable choices of paths. Okay, and that makes the analysis much more difficult. So the first breakthrough happened, construction of the metric for the case gamma equals to square root of 8 over 3 by Miller and Sheffield, Jason Miller, and in a series of famous works. Right, so what is special about gamma square root of 8 over 3? It is deeply connected to another metric measure space probability theory known as the Brownian map, okay, which was defined in separate but independent, but at the same time, these works came out from Jean-François Logal and then Gregory Mirmont. And so you have a lot of inputs also from random planar maps and things like that. The case of general gamma, subcritical gamma, okay, when gamma is any number between 0 and 2, remained a bit elusive. And then a program was launched, and the idea was as follows. Okay, I'll give the definitions, precise definitions later, but let's start with from the very basic, naive take on the problem. So you cannot make sense of a distribution, but anybody have aware of distribution theory and analysis. What you do in this case, you can make sense of, you can regularize this distribution to get well-defined functions, right? You can modify the distribution against, let's say, locally compactly supported functions with their support becoming going to 0, okay? And once you get a well-defined function, you maybe can try to define a metric using this length formula given by this tensor, okay? And try to see whether, the scaling, you can take their scaling limits, and that gives you some kind of non-trivial metric that you want. So this is a caricature of the program, which has taken several excellent work. So this is roughly the main strategy, which culminated finally in the construction of the metric. So step 1 is that start by producing candidate distance functions which are obtained as subsequential limits. So as I said, if you choose a particular modification threshold, epsilon, okay? So you convolve the distribution with respect to, let's say, a smooth bump function with support epsilon, or order of epsilon. You get an epsilon regularized version of this thing, okay? And then you have a one parameter family, okay, of random metrics, and you try to find their scaling limit. Okay, but of course, it's not clear whether the scaling limit exists first. So first, what you can best get, try to prove is that they are tight, at least, so that you can get subsequential limits. So obtain as subsequential limits of a family, the family I just described to you, of random metrics known as the so-called Liouville first passage. Percolation. Abbreviated as LFPP. Just a moment. Well, sort of, I think we kind of all know the definition of the classical first digit percolation on lattice. And if you think about it for a moment, it's not actually unreusable limb, because what you are doing here, essentially, if you remember how do you define a first digit percolation metric on discrete graph, let's say you assign some random weights to the edges, and you define the length of a path by just summing the weights along those edges of a path and optimize it, minimize it over all possible choices. Here, you're just doing that, but except in the continuum version. You define the length, the random length of a path by just integrating this thing with the, of course, by regularizing it at a certain threshold epsilon, and then you optimize it over all possible paths. That gives you the value of the distance. Okay, so that's a natural discrete analog. Finite threshold analog. Okay, so now what you have shown, so the first step you start from by showing that, well, these families of LFPP metrics are actually, with appropriately scaled, they are tight, so you can get the subsequential limits. Now, the goal is to show unique, their uniqueness of subsequential limits. This you do in two steps, sub-steps. All of them require very involved, different, separate papers. Step 2A, every possible, you somehow try to find out some common properties that every subsequential limit must satisfy. So every possible subsequential limit is shown to be a measurable function of the GFF, and that helps a lot, and that is very difficult. Satisfying a list of properties or axioms, let's call them, as they're called usually in this literature, list of axioms motivated by, move to the next one, yes, motivated by some natural, I'll actually go through them in the course of the talk, and you'll see they're actually quite natural. Natural properties and scaling behaviors. Scaling behaviors of the LFPB matrix. Once you have done that, then the job is to show, well, that these axioms uniquely characterize a metric. That's step 2b. Subsequently, these axioms are shown to uniquely, not only that, also it's shown that it satisfies some properties like it conformal invariance and other things that it, actually they're become even actually part of the axioms that you would expect in this situation from motivations from physics. So shown to uniquely characterize the limiting metric. Now, this entire program spans several years and works by many people. So let me just read their name. So Jian Ding, Julian Dubeda, Hugo Facone, big contribution came from, of course, Yuan Zhuan, Jason Miller, Joshua Pfeffer, and Zinsan. Okay. So this is for gamma belongs to 0 to 2. This is so-called subcritical. The behavior of the LQG metric is a bit well behaved in this region, okay, for this parameter range. For example, it's like equivalent to the Euclidean metric. In fact, actually, it is biholder equivalent to the LQG metric, Euclidean metric. Now, so let me talk a bit about parameterization, which will be relevant. So the gamma, as you see, well, let me get back to this original heuristic formulation. If you again remember this very basic Riemannian geometry, if you anyway, so for example, if you give the area form, this is basically this will be given if the area form is given by this with an exponent gamma, the corresponding length form you obtain by gamma dividing by the dimension, right? Underlying dimension. So that is the what actually should appear when you evaluate the length. Similarly, there is a notion of Hausdorff dimension of this constructed metric space. Okay, so when you define the length in this LFPP, when you want to obtain the length by integrating this exponential of the regularized field along paths, you cannot keep this parameter same as gamma, but this parameter, the so-called LFPP parameter, Z of gamma, at least for the subcritical, it is just this. And this is a true parameterization, which is also shown in the works. So which gives an alternative parameterization. Of the LPG metric. Although the explicit dependence is not known except for some bounds. Explicit dependence not known. Except from some cases, for example, the one corresponding to gamma equals square root of 8/3, where the dimension is just 4 for the Brownian map. You cannot. Anyways. So, what is the time again? How much did I spend? Okay, so I think it's okay. So, I'll not actually babble much about different parameterizations, but what is actually, there is another surprising fact is that there is another is that you can. So what does this subcritical, the supercritical or critical regime correspond to? They correspond to the values of gamma. So when mod of gamma lies in the unit circle, the mod of gamma equals to 2, gamma belongs to C. Okay, so that corresponds to the supercritical and critical regime. Although you can immediately make sense of this metric tensor, you can nevertheless make sense of this parameter xi, which will range over now. Here, actually, it will be a bounded range. It will just range over any real positive real number. And in this regime, it was subsequently constructed, the metric, but although it's much more singular, by series of works by Jian Ding, Yuan Zhuan, and Joshua Pfeffer. Okay, that's I think enough as an introduction. But along with the existence of the metric, several other geometric properties started to be studied. First of all, it was shown that the geodesics exist. And not only that, what is interesting is that they are, which is a bit more non-trivial, is that they are unique, almost surely. And the most relevant one for today's talk is a paper, is a work by Joshua Pfeffer, and Scott Sheffield. Where they showed the following, that there exists a deterministic this is a 0-1 law, deterministic constant. Let's call that delta geo function positive for all gamma in 0, 2. There is an equivalent parameterization of the xi. Says that such that almost surely the Euclidean positive dimension of every gamma LQG geodesic let's just start it from a point. Is equal to delta geo. Okay. Now, it has been long been believed. I mean, there is sufficient reasons to believe that, because anyways, things are rough, and that this, if it did exist even, it will be strictly bigger than 1. And there was a paper, the closest, the result before actually this one, was the result by Jianding and Fuxi Zhang, where they obtained an analog of this result for Liouville first phase calculation distance. And that was quite technically involved. But now that you have all the tools, the metric has been established, all these axioms, it turns out that you can find a very nice proof of this fact. And that also conditional result, because it didn't work for all the values of parameters, even in the subcritical regime. So it turns out that actually you can find a very nice, elegant proof, short proof of this fact, of this folklore belief for all values of this parameter, okay, xi. It doesn't matter, it's supercritical, subcritical, subcritical, all at once. So this is the main result. By the way, just remember, it's, of course, Euclidean Hausdorff dimension, because, of course, if you, in any length space, if you find the Hausdorff dimension with respect to the intrinsic metric, it will be 1. So that's nothing to add. Okay, so that's the theorem. So let H be a whole plane GFF. And H be the metric with the associated Z OQG metric. Then for all Z bigger than 0, almost surely, and simultaneously for all geodesics, the Euclidean Hausdorff dimension for any DH geodesic is strictly larger than 1. Okay, and there are different other variants. As I said, others have been using this term variance of GFF. So this is a whole plane GFF, which is particularly convenient to work with. But you can actually take other versions of GFF, like those on a, let's say, on a disk and thing. But the result will follow because they're mutually absolutely continuous with respect to each other. I mean, yeah. Z and gamma. So Z, at least for the subcritical regime, is gamma over d gamma, which is what sits in the parameter in the exponential when you define the LFPP lengths. That's how actually the correspondence. But of exactly, because for gamma complex and all this thing, then yeah, so that's how it should make sense. Okay, so just look at the time based on that. I just regulate the list of the talk. So it's like okay, so let me just start with the main idea of the proof, and then actually I'll probably get back to the background story at the end if time permits. Okay, so what is a naive way to show that some Hausdorff dimension is bigger than 1, strictly bigger than 1? Well, the idea is that it fluctuates from a line, let's say a straight line, or it deviates from a straight line like behavior in a nested sequence of scales. That's a very naive, and that's a very also very fruitful way of thinking about it. To this end, there is a celebrated paper by Eisenman, Michael Eisenman, and Burchard from late, I think it's 1997, which says, and it was being used actually from the SLA literature, for example, a lot. Beautiful paper. The idea is something like this. So suppose, and it actually applies to a system like this very nicely, when you actually want to prove something for a system of curves simultaneously. So suppose you have a random, it doesn't have to be some property, so let's say a random family of curves, okay? And it has the following property. So let's say you put disks. So let's say, put this annulus of some aspect ratio. Let's say this radius is the half. So let's say this is R over 2, and this is, let's say this is R. Okay, R can be anything. Let's say we are working in a compact subset of the plane. It doesn't have to be again original result for plane. It could be any grid in space, but let's just, because we're working on plane. So of anywhere of any size, but the same aspect ratio. So here, anywhere. Now let's consider this event that a path in your system of curves called P does this. It simultaneously crosses, where by crossing I mean that that of course it will have both these endpoints on the outer boundary, and it will intersect the inside disk. Okay, so let's say it does that simultaneously. Okay, let's say their number is n. If the probability, so it's a big event, of this entire event, so the event is that any path does this. Okay, it doesn't have to import. Any path in your system does this for, let's say, a given family, given a system of such anywhere located disk, but which are well separated. Let's say that's the thing, that the distance between any two is at least the order of the maximum of their two diameters. Okay, that's what well separated naturally means. If this probability decays exponentially in the number of annuli, if you have that, then you can prove that the Hausdorff dimension of any path in this family is strictly bigger than 1. And you can also obtain an explicit bound. However, this is not true. I mean, okay, I mean, this original application was done, kept in mind this, things in the lattice spin models like percolation and the interfaces in percolation models where you have independence, two-dimensional percolation, critical percolation. But here you don't have this thing. In this, I mean, one of the main challenges, of course, in the entire business was find out efficient ways of dealing with dependence. But it turns out that you don't have to be so stringent. You don't have to be so stringent. What you have to do is something like this. So here is a thing. So let me just say reformulation of AB, Eisenman-Butcher, 97, which you prove. But the thing is that there is a certain, for a certain restricted arrangement of annuli, the same probability as this one, let's call it star, probability star is less than or equal to so essentially okay, let me just write it down. It's like e⁻ minus c something. Don't bother much about these factors, but what is mn nu? So mn nu is roughly that where n is roughly m nu. So what does nu? Nu would be some finite constant. Nu would be essentially what will happen is that what we'll assume, this restricted condition, is that instead of allowing the radius to be anything, we'll just assume they are kind of evenly distributed amongst a sequence of scales, m many scales, and roughly in each scale you have roughly nu many disks. It's kind of balance, regular condition. So this is enough. Okay, it's not quite exponential decay, but that's all you can prove, and that's enough. So in the remaining 15, okay, minutes, let me just describe the main idea of the proof, which is very simple. Then if time permits, we'll go to the other things. But so let's just see how to prove it. So there are two steps. First, to see that no matter what the radius is and center is, the probability that a path at least crosses this, it's uniformly bounded away from 1. Okay, that is strictly less than some constant depending only on the underlying parameter. And here actually lots of axioms of the Liouville quantum gravity come into play, but this is very simple. So here is the idea. So I have to draw lots of disks, so that's okay. So let's say one disk. Yeah. No. Yes. That's the thing important. Yeah, they are different. They are very different. Yes, so the separation is essentially, well, the distance would be the order of the maximum of their radius. Yeah, I mean, well, let's say, let's take that if you take a twice bigger and twice bigger, they don't know. That's all, simple as that. Okay, so let's say this one. This one. And another one. This part I'm always scared by, drawing so many circles, concentric circles, but in front of everybody. But this is not circle, but bear me with that. Yeah, that's okay. Okay. So the scale, don't this statutory warning. Don't mind the scales, but so this is supposed to be R. Let's say R over 2. This big radius, it's R. And let's say these are some intermediate radius. So this is, let's say, just Ri just increased by R over 8. So I think this is just 5R over 8. This, again, this fellow here is 3R over 4. Finally, this guy, 7R over 8. So I'm just increasing every radius by R over 8, just to presume. Okay, so here is the thing. Suppose what you want to say, you want to prevent this event. You want to prevent from a geodesic from doing this. Well, one naive way is the following. Suppose the distance across this annulus in this metric, okay? Distance across this modulus in this smaller annulus is actually bigger than the distance around this red annulus. So let me, which is outside. So, okay, so this event I'm looking at. So let's say Z being the center, the event is that the LQG length of this this annulus around. So what I mean by this length, which is that the minimum DH length with respect to this metric of any path that separates this disk from this outer disk. Okay, that's all. Is strictly less than DH of this distance across. So this is that small. Well, if that happens, then you can immediately see, because geodesics are length minimizing, it doesn't really make sense for it come all the way here. I mean, I can just write this point because it's planar. So anything has to, which crosses annulus, and since it's a circuit, it has to intersect. So what I can do, I can reroute the geodesic like here, and then go. Well, what do I do, and what do I gain, and what do I lose? Well, of course, I can, the increment in length can be at most the length of this red annulus. However, the one I save is the length of the distance between these two, which I have to do, right? Because I'm coming from outside, I'm at least have to cross this white and blue annulus. So on the event GZR, the geodesic can never actually come inside, okay? So it can never cross. So this is the event. So all you have to show is that all we need is just the one ball case. is to show that probability of GZR is let's say it's bounded above. Sorry, it's that's right. It's yeah. I just want to show that this is some constant depending on xi bounded away from 0. That's all I need, right? Again, how much? Huh? Okay, that's good. That's very good. Okay, so what are the steps of proving it? Step 1. It's very simple. Is that show that probability of this event, which a priori depends on the center of the ball, and it also relates to our first question. It also depends on the a priori depends on the radius, is independent of ZNR, which is not immediately clear. That is, we just want to show that the probability of this event GZR is just, I just take away the dependence on especially R, that is the most standard one, G01. So G is, let's say, like xi or what? Oh, Z is the center. Z is the center, sorry. Z is the center, R is the radius, the biggest one. Okay. All right. So here comes one of the, as I told you, the metric is characterized by a list of actions. Here's one, the first one I'm going to, and as I told you, I will actually relate them as they are required. It's called the so-called well scaling. So this is the property. This is one of the characterizing properties. So let me just write it. For a random continuous function f defined on the complex plane, real valued, define this tempered version of this metric, the distance with being acted upon by e to the power ZF as usual infimum over. So this is as if like what the metric would behave like if you added a continuous function, okay, to the field. So remember, it is like e to the power xi times h. So if you add a function h plus f, e to the power xi f will come out, okay? So that is basically the idea. So w integral to 0, the dh length of p, e to the power xi, and it's very natural. I mean, it's exactly what we would expect, dt, because the function can vary, of course, along the path. That's why you have to do it this way. For all z, w, and c, where the minimum is over all dh rectifiable paths. So if you define this, then what it says is that then almost surely e to the power z8 zf dot dh, this new tempered metric, is essentially dh plus f. I mean, one of the actually one of the breakthrough understanding and basically finally settling this problem is this relation, and I mean, just floating around and then materialized by Joan and Miller, was that you cannot just look at the metric defined by a Gaussian free field, but you have to do it with h tempered by a random continuous function. That did marvel. Yeah, for all f, c, r, continuous. Okay, now, So how that help us? So what it means, in particular case, when f is constant in a region, okay? So let's say, right. So then what would happen is that the metric will just get multiplied by a constant. That's all, okay? But we are just, so if let's say I temper the metric by adding a constant to the field, at least on this region, then everywhere the metric will just get multiplied by a constant. And since we are only dealing with comparisons, right? It's just about comparison between two distances, not their absolute values, but their relative values. So the event will remain unchanged. So brings us to just probably ask more minutes, then actually I'll finish. So what I'll do is that, and it's because, okay, so here is the thing, because you see, you might think when actually you're trying to get rid of R, you might probably think about using some kind of invariance properties of Gaussian free field. But there are some properties, but it's not so simple. And that's why you have to go to this trick. So the invariance property that you have for open Gaussian free field is this. HRZ is equivalent in law to H dot minus H1 of 0, where this is the circle average. So it's you can make sense of integrating the field with respect to a circle of certain radius centered at a point. Okay, so the point is that what you can do now is that I can subtract HRZ without changing this event, and that is then actually I can get rid of the dependence on R and Z. Okay, so that's basic idea. So then that part is done. Then 2 is the idea that, well, we have to show then probability of G01 is strictly bigger than 0. And here is the sketch. So how we can do that? How you can show that, well, there is a positive probability that the distance across this annulus is bigger than this much bigger, this circuit. Okay, so there are 2 things here. First is that maybe I just write the notes here because there are not much time. It is known, this is a part of the thing, it has been proved, it is known that these random variables, dh across and dh around are finite and positive random variables almost surely. Positive almost surely. So what it means that, well, with a positive probability, the distance around can be at most some constant. Let's say big constant, depending on size of this, the length of this blue, right? Okay, but you exactly need this. You cannot have just any constant, you have just one. Okay, so there we'll do this trick. That is always used in Gaussian processes, which is that you shift the mean locally. It's known as the Cameron-Martin theorem. It's just nothing but the infinite, the change of mean version for infinite dimensional Gaussian spaces. Theorem. So the idea is the following. What do? You add a bump, you add a compactly supported function to your field. And by this well-scaling property, we can always evaluate their, the effect. I mean, that's easy. What you do is that this. So, I want to increase the field value here. So let's say here in this inner circle, I add something, some big number. Let's say C, which is never, which will depend on this ratio that we have. Let's say some a priori. So let's say with the C prime, I have a probability of this thing dh or this less than C prime times dh of that. is bigger than 0. Okay, so it will based on this C prime, which is supported inside this ball of radius, this inner red disk. In particular, it would be completely 0 here. So the distance here will not be changed. Okay, so now what happens is that on this disk, this distance by this world scaling would get multiplied up by this constant. Okay, so then by this formula on this event, then what will happen is that with respect to the shifted fields, so let's say H plus some C times phi, some bump function, the probability of the same event without of this event with H replaced by H prime would be positive. Now the thing is that you can, by Cameron-Martin formula, control the random-Nikodym derivative, okay, of this for this change of variable, okay, which will give you an uniformly from this observation a uniformly positive probability that this even actually happens for H, okay, instead of H prime. All in all, what you can show is that ultimately is that the probability that this GZR happens is bounded away from 0. Well, then the job is, of course, to replicate it over a well-separated family of disks, okay? And I'll just end up with the, I think probably it's almost over, right? What is the problem? The problem is it's not independent, okay? They're heavily dependent, but they're dependent in a nice way. What carries the dependence if you put one ball here, let's say, and another ball up there, you can actually decompose the field into 2 parts by what is called the Markov property of Gaussian field, or Markov decomposition, let's say. I think that's a term. So what this allows you to do is to write the field as a sum of 2 parts. One would be completely local to this disk, okay? And so that's why actually we take this disk well separated, okay? So their local fields will be completely independent, shielded from each other. So the entire dependence is carried by what comes, this lays on the top, which is the harmonic extension. That's heavy, but so there is an important property. The harmonic average, again, is a singular thing, object, okay? So what helps you? Well, is this observation that I've been repeating. None of this business, you see, the absolute value of the distances matter because I'm just comparing distances. So even if the harmonic, this field on this one is very big, it doesn't matter, for example, if they are constant, right? Because, by well scaling again, if I just added a constant, everything will be multiplied by the same number. So, whatever was there before, it will still continue to hold. And so what really matters is controlling the regularity of the harmonic field within these disks simultaneously. Okay, so there are 2 components in this probability. One would be geometric, which is good, which is the independent thing, just like percolation. The other would be coming from the control of regularity of the harmonic averages of this field across a system of this disk like this, which basically gives you this suboptimal decay, but that's good enough for us. Anyway, so that's sort of the rough overview. Thank you.
One quick question, maybe, if anyone has a question. All right, I guess everyone is hungry, so no one is willing to ask questions. All right, so so this is lunch. We will reconvene back at 2:30. Lunch is just outside. Okay, so just in the foyer outside. All right, okay, we'll see you in the afternoon session.